Okay, so we are back here to talk about the reactivity series of metals. So this is metals lesson 2. So the previous lesson, we said that metals take up most of the periodic table. If you look at it, almost two-thirds of elements are metals. Okay, and metals are quite interesting because they are used widely throughout history to make weapons, tools, machinery, and so on. But not all metals are the same. In fact, metals differ in terms of their reactivity with other things, right? Some metals are just reactive and explosive. Some metals are very unreactive. They do not react with water. They don't react with oxygen in the air. They also don't react with acids. Okay? So metals really come in different shapes and forms. They have different properties. And so we came up with the idea, can we order the metals in a reactivity series? All right. Starting with the most reactive metals on top, least reactive metals at the bottom. Okay. So this we should know well. Okay. Now my question is, so are all the metals in the periodic table in the series here? Well, obviously not, right? So there are many metals that are not listed here. But can they be slotted into the reactivity series? The answer is yes. All right. So I'll give you an example. One of the common metals we also deal with is chromium. Chromium is an interesting metal, but chromium is not in this series. So how do we decide which position should chromium be? Well, we can do experiments to find out. What are the experiments we can do to find where chromium should be slotted? Well, we have learned a few reactions of metals last lesson, right? Last lesson, we learned that metals can react with cold water. Some metals can react with steam. So we can try to react chromium with water and see what happens. We can also try reacting chromium with steam and see what happens. And that's the idea, all right? In order to work out the order of reactivity, we always do experiments. And the experiments will always revolve around the reactions that we learn in this set of notes. Okay? So I won't go into the details of the planning yet. Okay, we'll do that in further detail next year. But I just want you to know that we do experiments to find out how reactive a metal is. And the experiments we plan and do are basically the reactions we have learned. Okay? Now, so for these metals listed here, they are the most common metals. That's why we list them here. All right? And the most reactive are found on top and the least reactive at the bottom. How do you remember this order of metals? Well, there's an acronym, right? P, sand, cat, monkey, and cute zebras in large heated cages soon. So potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, lead, hydrogen, copper, silver. All right. Now, this is the bare minimum. You need to remember this series. All right. You have to remember it. And this series will also be important later on when we do electrolysis. So please spend some time to memorize this series. And we also talked about the reasons why we inserted carbon and hydrogen into the series. Carbon and hydrogen, they are non-metals. They are not metals. But they are inserted into the series for reasons, good reasons. So as we'll see today later on, carbon is inserted into the series because based on where carbon is, I can work out whether the metals can be reduced by carbon or not. Metals above carbon in the reactivity series cannot be extracted by reducing their oxides with carbon. So take for example, magnesium is above carbon. So magnesium oxide plus carbon, no reaction. Magnesium oxide, if I heat it up with carbon, no matter how much I heat, there will be no reaction. So we say that carbon is unable to reduce magnesium oxide to magnesium. Whereas something below carbon, for example, if I use lead oxide plus carbon, there is a reaction because carbon can reduce lead oxide to lead. Okay, so the relative position, whether it's above carbon or below carbon, will determine whether its oxide can be reduced by carbon. And that's the reason why we put carbon in, so that it's a reference point for us to tell whether something can be reduced or not by carbon. Hydrogen is also a useful reference point because we know that metals above hydrogen can react with acid. Metals below hydrogen, like copper, cannot react with acids. So those are the two reasons why we insert carbon and hydrogen into the reactivity series. Okay. And what else did we do last lesson? Well, we spoke about the reaction of our metals with cold water. By cold, I don't mean ice cold. Something like water from the tap, water at room temperature is also considered cold because there's no heating, right? I didn't heat the water up. So metal plus water gives you the metal hydroxide and hydrogen gas, all right? And we went through how to describe each of these reactions, right? Potassium reacts very violently with water to form potassium hydroxide and hydrogen. Sodium reacts violently to form sodium hydroxide and hydrogen, and so on and so forth. All right. Now, the learning point that I want you to get, two things. One, when you react with water, you get the hydroxide. Okay. Two, the second learning point is only the top four most reactive metals react with water. This is very important. All right. So I think last lesson I spoke about this. If you read, magnesium reacts very slowly with water. Does it mean that magnesium is unreactive? No. In fact, the fact that it reacts slowly with cold water means it's quite reactive, because it actually reacts. As compared to other metals like iron, lead, they don't even react with water. Therefore, we can conclude magnesium must be one of the more reactive metals in the series because it reacts with water, despite it being slow. Okay. Then we also spoke about steam last lesson. Now, steam, importantly, you need to realize that steam is hot. It's basically boiled water. Water has finished boiling, meaning steam must be at least 100 degrees or higher. So it's a high temperature. So obviously, with a higher temperature, your particles have more kinetic energy to move faster and collide more often. As a result of that, when you use steam, you realize that more metals can react. Just now, only the top four metals can react. Now, all metals until iron are able to react with steam. This goes to show that steam, higher temperature, does promote the reaction of the metal with steam. The second point is when you use steam, you form the oxide. So just now, water is the hydroxide. When you use steam, it's the oxide. Okay? And you can see last lesson, we already went through the description, the equations for each of these reactions. Okay? Now, last lesson, I left you with the iron, of course. Now, iron, you can notice that it's quite a unique situation. Firstly, iron is less reactive than zinc or magnesium, right? Iron is below zinc and magnesium in the reactivity series. So iron, in order for it to react with steam, you need to heat it up to a high temperature. So you need to have red hot iron. Red hot iron is actually very high temperature. It's so hot that it glows red. And despite that, the red hot iron reacts slowly with steam to form this thing called iron tetroxide, Fe3O4. So I mentioned that Fe3O4 is basically FeO, the iron 2 oxide, and Fe2O3, iron 3 oxide. So a mixture of both iron 2 oxide and iron 3 oxide are formed, all right, when iron reacts with steam. Now, what's the reason why? Now, to be really honest, I must confess, I don't feel that I have a very definite reason why it forms iron tetroxide. But one important reason could be that because this reaction is quite slow, all right, it takes a long time to happen, your iron 2 oxide, some of it can oxidize to iron 3 oxide. but not all of it, because it takes a long time. There's a long period of heating needed. And therefore, some of the iron 2 oxide can oxidize to iron 3 oxide. And that's the reason why you end up with both products being present. Now, so why is it that we combine the chemical formula to Fe3O4? This is because the ionic lattice contains both iron 2 oxide and iron 3 oxide. They are actually chemically bonded together. That's why we combine the chemical formula into Fe3O4. So it's one of the more interesting examples of a double ionic compound. This means that within the ionic lattice, there are actually two different ionic compounds, but they are now chemically bonded together. Okay, we won't go into the details of this because obviously it's more complicated study of the crystal structure. But just know that for iron, it forms Fe3O4 when it reacts with steam. Now, this is also a reversible reaction. You can tell from the double direction arrow. Again, a signal to you that, hey, this reaction is probably pretty slow. And this is also evidence that iron is less reactive than zinc or magnesium. Okay, so we stopped here. Now, last lesson, I did not move on to these questions for a good reason, because I want us to revise and begin with this. So how do we actually react metals with steam in the lab? You must be wondering, like, how do we even do that, right? Well, this is a setup. This is a setup to react metals with steam in the lab. So basically, we actually fill a test tube or boiling tube with powdered metal, and we have glass wool soaked in water. Now, what is glass wool? You all have seen cotton wool before. Cotton wool is obviously made of cotton. Glass wool is wool made from glass. Okay, so glass wool is almost like cotton wool, but it's made from glass. So you need to handle it properly because you don't want glass wool to break in your fingers. All right. So glass wool is very useful because it withstands heat pretty well. And obviously this setup involves heating. So basically you just put the glass wool into water, soak it, then put it into the boiling tube. And then you heat. Now, please notice you heat the metal. You don't heat the glass wool directly, right? You're heating the metal. Because if you think about it, what requires heating? What requires heating is the metal, right? The water can boil quite easily because water has a low boiling point. So you don't have to put Bunsen flame at the water. You should put the Bunsen flame at the metal, okay? So obviously the water will boil at 100 degrees Celsius to form steam. So the steam will pass over the metal. So the steam will pass over the metal. So we commonly say that a stream of steam is passed over the heated metal. Okay, so that's when the reaction will occur. So obviously this reaction produces the metal oxide. The metal oxide is a solid. Because it's an ionic compound, it will have a high melting point. So it's a solid. So the metal oxide is a solid, it will stay in the tube. But obviously hydrogen gas is also produced. So how is the hydrogen gas collected? Well, in this method, it's collected using displacement of water, right? You can see that the hydrogen gas is produced, goes in, comes here. So this is the hydrogen gas. And where did it come from? It was produced from the reaction. Okay, so that's how you would collect the hydrogen gas using displacement of water, which is perfectly fine because hydrogen gas is insoluble in water. So since the gas is insoluble in water, you can use displacement of water to collect it. Okay. Could you have used upward delivery? Yes, you could have. Okay. Now, so let's go through the questions. Now, these questions are important. Okay, they are not put here for fun. There's a reason. So the first question, it is not recommended to react potassium and sodium metal with steam. In fact, if you saw my table on the previous page, I actually only started with magnesium. All right. It is actually quite dangerous to react calcium with steam as well. All right. But potassium and sodium definitely is not recommended to react with steam. Suggest why this is so. I think it should be clear cut. potassium, and sodium are highly reactive metals. And let's link this to the reactivity series. How do you know from the series they are very reactive? They are highly reactive metals at the top of the reactivity series. So they react explosively with steam. So if it's explosive, clearly it's unsafe to carry out. Okay, so that's the first question. The second question, zinc. Zinc is an example of a metal which doesn't react with cold water, but it will react readily with steam. If you were to heat up, okay, the zinc with steam, it reacts readily. But why? So suggest why less reactive metals like zinc are able to react with steam. So this one, we briefly alluded to it. It has to do with the fact that steam is obviously at a higher temperature. Than water. Okay, we mentioned steam must be at least 100 degrees or more. So steam is obviously at a higher temperature. So what happens when you have higher temperature? Particles have, or rather, so more particles have sufficient kinetic energy to collide and react. Okay, both in steam as well as in the metal. More particles will have sufficient Ke to collide and react. That's why they react. Okay, so usually, right, the less reactive metals, they actually need more energy. The particles in the less reactive metal, they require more energy to react. So by providing steam, you are providing a higher temperature, which equates to more energy. Okay, now question 3 is always the question that most students will ask. And sadly, not every single teacher knows the answer for this, okay? Or not every single teacher may explain why. Now, there's a reason for this. Why is it that when you use steam, you produce the oxide and not the hydroxide? So let's recall what is oxide? Oxide is what? Oxide is O2 minus, right? Hydroxide is different. Hydroxide is OH minus. So between these two ions, oxide, hydroxide, which one is polyatomic? Which ion is polyatomic? So if we look at it, oxide has only oxygen. Hydroxide has oxygen and hydrogen. So OH minus is polyatomic. Now, the interesting thing about polyatomic ions like hydroxide, carbonate, nitrate, sulfate, these are all polyatomic. The interesting thing about polyatomic ions is that under the right circumstances of temperature, they can decompose. And that's the reason why you have learned carbonates can decompose to form the oxide and carbon dioxide gas. Because the CO3 2- can decompose. Similarly, sulfates, nitrates can also decompose when heated to the right temperature. So OH minus hydroxide is also no exception. When you heat it to the right temperature, it will decompose. When a hydroxide decomposes, what is formed? Well, what is formed obviously will be the oxide. So now let's recall. So steam is hot, high temperature. So what did we just say? High temperature is steam. Can we link this high temperature to the hydroxide decomposing? The answer is yes, because at high temperatures, like steam, for example, the hydroxide is less stable and decomposes to form the more stable metal oxide. And I hope you will remember this. This is a key concept. So regardless of what you're looking at, be it the nitrate, sulfate, carbonate, hydroxide, when you heat up these polyatomic ions, they will always give you the metal oxide as a product. Okay, for most metals, about 80% of the time, when your hydroxide, nitrate, sulfate, carbonate decomposes when heated, it should give you the oxide as a product. This applies 80% of the time. We will talk about what's the 20% of the time another time. Okay, but most of the time, the stable product form is the oxide. And the reason is because the hydroxide is less stable. So when you have high temperatures like in steam, hydroxide decomposes to form the metal oxide. Okay, so that's question 3. Now, so far, you realize that it's all to do with the reactivity series. It's all to do with steam being at high temperature. Okay. Now, question 4 is more of an experimental thing. Okay, so for question 4, I would like to point you back to the diagram on top. So what is question 4 actually talking about? Question 4 is talking about the delivery tube. The delivery tube I shall highlight in yellow is this tube. The tube that delivers hydrogen gas into the water. That's called a delivery tube, right? Now, it is important to remove the delivery tube from the trough. The trough is where the water is. Okay, so in case you didn't know what's trough, trough is basically a tub of water. Okay, so you need to remove the delivery tube from the trough before switching off the Bunsen flame. So you remove the tube already, then you turn off the Bunsen flame. Now, what is the issue? How come this is important? Right? So let's think. What is the delivery tube delivering? The delivery tube is delivering hydrogen gas. Right? If we were to switch off the Bunsen flame immediately without removing the tube, what might happen is that, remember, the tube is hot. Even after you switch off the Bunsen flame, the tube is still hot. It has been heated for a few minutes, right? If the tube is hot, what can you say about the pressure inside the tube? All right. If you think about it, when you have a fixed amount of a gas, all right, and okay, the tube is still hot inside, what happens is the pressure will be low, which means that any gas around outside will be sucked into the tube with the metal. So there is gas around it, right? There is hydrogen gas at the other end of the delivery tube. So if you don't remove the delivery tube, the hydrogen gas and potentially the water as well will be sucked into the original tube with the metal. Now, you have already encountered this. If you recall, when you did the QA practical in the lab, you were decomposing the carbonate in one tube, and then you connected it to lime water. Why lime water? Because you want to test for CO2, right? Some of you, your lime water got sucked backwards into the carbonate. Okay, I think a couple of you had that. Your lime water got sucked up. And the main reason I told you was that, oh, because your original tube with the carbonate was heated too strongly. You didn't move in and out of the flame. And that's the idea. It's the same here. If the tube is hot, the gas is sucked backwards. Okay? If you switch off the heating, same here. So always you must remove the delivery tube. It is to prevent the hydrogen gas and also the water from being sucked back into the hot tube. Okay, this is just an experimental consideration. Okay? Okay, will the exam test this? Yes, you are supposed to know the experimental setup, how to set it up, why is the setup like that. Okay, so don't just memorize, make sure you understand it. Right? Now, moving on, the next reaction. So we have learned so far metals with water, metals with steam. Third reaction. The third reaction is very easy. It's metals with acid, specifically hydrochloric acid. Okay, so if I can move on to the next page, can you please give me a thumbs up so that I know that you're finished? How about the rest? I don't see a lot of thumbs ups. The rest, Audrey, Rishi. Okay, now I shall move on. Now the third reaction, this is reaction number 3 already, metals with HCl. I'm sure you know this reaction. You have learned it even in Sec 2, right? Acid plus metals form salt and hydrogen. But this is HCl, so the salt is called the chloride. So it's the metal chloride. And hydrogen gas, of course. This one you have learned in Sec 2 also. You have even learned how to use this reaction to produce hydrogen. You have also learned how to test for hydrogen, right? Insert a lighted splint into the mouth of the test tube. Okay. Now, remember under acids and bases, we actually taught you that certain metals are unreactive. So which metals don't react with acid? Actually, all metals above hydrogen can react with acid. So where is hydrogen? Well, hydrogen is here. Hydrogen is above copper. So everything above hydrogen can react with acids. Okay, can react with acid. Of course, anything below hydrogen cannot react. And that's the reason why under salt prep, we keep on telling you to make copper salt, you can't add copper metal into the acid. It wouldn't work because copper metal doesn't react with acid. It's below hydrogen in the reactivity series. Okay. So now let's go through. So obviously potassium and sodium, again, they are explosive with acids. And that's the reason why to prepare potassium and sodium salts, if I want to make sodium chloride, I'm not going to add sodium metal to HCl. It's explosive. It will give NaCl, but you can't collect it because it explodes, right? If it has exploded, there's no way to collect the salt. Therefore, we do not add metal to acid to make sodium chloride. To make sodium chloride, potassium chloride, we will use a titration. So hopefully this gels with your understanding of salt prep. We keep on telling you, spar salt, use titration. And this is the reason why you can't make sodium and potassium salts by reacting them with acids. It's explosive, it's unsafe. All right? You want to make the salts safely. Okay? So sodium and potassium, explosive. Next, we go to calcium. Now, calcium reacts very violently with hydrochloric acid And this forms obviously calcium chloride and hydrogen. Okay, I think writing the equation shouldn't be difficult by now. Let me just quickly write it for you. Okay. So this is the reaction between calcium and hydrochloric acid. Now, next one is magnesium. So we have learned before. Very violently. The next one will be violently. And you have tried this in the lab before. Magnesium, if you put just one strip of magnesium into HCl, the reaction is actually quite violent. Huh? The effervescence is really vigorous. The tube gets very hot. All right. So this is an example of a violent reaction. It forms magnesium chloride and hydrogen. Okay. So again, I think this equation is not difficult to write. Okay. So very violently. The next one, what do you think the word would be? Zinc. Zinc reacts readily with HCl to form zinc chloride and hydrogen. Okay. So let's remind ourselves, zinc forms Zn2 plus. So zinc at first got no charge plus HCl. Zinc chloride is ZnCl2. Okay, plus hydrogen gas, H2. Next, iron. Iron is less reactive than zinc, right? So let's go in order. We started with very violent, then violent, readily. So the last one, slowly. So I'm teaching you how to learn. Okay, learn the words properly. So iron reacts slowly with HCl because iron is less reactive than magnesium or zinc. So it forms, okay, importantly, it forms iron 2 chloride. Okay, so iron, metal, slow reaction forms iron 2 chloride. Okay. Now, most of you will then ask, huh? But I thought iron also has iron 3. You're absolutely right. Okay. So my question is, what color is iron 2 chloride? Well, clearly, iron 2 chloride, you've learned, iron 2 is green. So this is a green solution. But does the green solution remain green for very long, forever? The answer is no. Once iron 2 chloride is formed, if it's exposed to air, what will happen is iron 2 chloride can oxidize to iron 3 chloride. And so you will see the green solution turning yellow or reddish brown. And that's because it has oxidized. But the first product that's formed is iron 2 chloride. Okay, so over here, we are just talking about the first product that's formed, which is iron 2 chloride. But yes, you are right. If exposed to air, then the iron 2 chloride can further oxidize to iron 3 chloride. That's later on. Okay. Now, up to this stage, I think it's quite straightforward. Okay. In fact, I think under the balancing of equations, we have also done questions asking you to write the general equation for the reaction of a metal, a group 2 metal with HCl. So a group 2 metal with HCl, you can see the mole ratio of the metal to HCl is 1:2. Okay. Now, the reason why I put lead right at the bottom with an asterisk is because it's quite unique. Now, lead, Pb, lead is above hydrogen. So lead will react with HCl. Lead reacts very slowly. All right. It's very slow because it's even less reactive than iron. But the important part is you need to know this. It only reacts initially, but the reaction will stop completely after a short time. Meaning the reaction doesn't continue on forever. It's a very slow reaction, but it stops after a few minutes. The reason is because if you think about it, lead will form what with HCl? Lead forms lead 2 chloride. If you think about the solubility rules all chlorides are soluble except the LS, right? Lead 2 chloride, silver chloride. So lead 2 chloride, silver chloride, LS, they are the insoluble chlorides. Because they are insoluble, this means that the lead 2 chloride is a precipitate. It's a solid. So how do you write the equation? Well, lead plus HCl, it will form lead 2 chloride, PbCl2, but PbCl2 is a solid. It is not aqueous like the previous few metals. So because it's a solid, this has important consequences. So now if you think about it, if I put a piece of lead metal into HCl, it forms the lead 2 chloride. The lead 2 chloride is a solid. It has to be deposited on the surface of the metal. So the lead 2 chloride is a solid that coats the entire surface of the metal. And the result of this is that if it coats the whole surface, the metal inside cannot react further because the metal inside is no longer exposed to the acid. All right. And that's the reason why the reaction stops, because now you have a coating of lead 2 chloride. And therefore, it will stop the reaction from happening because it prevents the metal from coming into contact with the acid. Okay. Okay, up to this stage, are we coping? Do we have any questions that you would like to ask? Okay, Jet thumbs up is okay lah. Then the rest, do you have any questions you would like to ask at this stage? I know I've gone a bit slowly, but that's the point. No? Okay, so I shall ask a question. If you notice, right, there's something that's clearly missing. If you look at the series of metals, we always have left out one metal from our discussion. There is actually a metal between magnesium and zinc, right? Aluminium, right? But we have left it out conveniently, you know, as we talked about all the reactions. Well, does aluminium react with water? No, aluminium doesn't react with water. But will aluminium react with steam? Will aluminium react with acids? So let's hear from a few people. Okay, Jing Kang, do you think aluminium will react with steam?
No.
No. Why not?
I don't know.
No, must be supported what? By evidence.
I think it's the same as lead.
Lead,
The same explanation as lead.
Oh, so does it react? Because when you say lead, right, actually lead reacts with acid, right? Just that the reaction stopped, right?
Oh, yeah.
Okay, so does aluminium react with steam? Let me ask you again.
I think yes.
Okay, so thinking is one thing, supporting with evidence is another. So you notice that aluminium is in between magnesium and zinc, right? This means that aluminium is more reactive than zinc. So if zinc can react readily with steam, aluminium, being more reactive than zinc, should definitely react with steam. Okay, so this is how you use the reactivity series to predict. So aluminium reacts with steam for sure, because it's more reactive than zinc, and zinc can already react. So similarly, if we go back to acid, it's the similar situation. Aluminium can definitely react with acids because aluminium is above zinc. Aluminium is above hydrogen. All metals above hydrogen should react with acid. Okay, so that is the idea. Aluminium can react with both steam and acid, as shown by the reactivity series. Okay, so why is it that we have conveniently left it out? Not that we want to leave it out, not that it doesn't react, it reacts. All right, so over here, I would like you to take down, aluminium is quite unique. Most of us tend to think of aluminium as something that is quite easy and safe to use. We use a lot of aluminium at home, for example, aluminium foil. It's a good example, right? Now, aluminium, it actually reacts with steam and also acid. It will react. However, if you use aluminium metal, the reaction is slow at the start, but becomes faster and more violent as it proceeds. Now, this is a trademark, a very unique point about aluminium. All right, any reaction with aluminium metal itself is slow to start, but it becomes faster and more violent as the reaction proceeds. Why? Okay, Jinghe is not wrong. I think the explanation is quite similar to lead in some sense. Now, the aluminium foil that you buy as a roll, right? The aluminium foil is aluminium metal. Now, aluminium metal is quite reactive, just like, say, magnesium. When it comes to you in that box, the aluminium has already reacted with something in the air. Well, there's a lot of oxygen in your air. So what has happened is that the aluminium reacts with oxygen in your air to form a layer of aluminium oxide. So every time you buy aluminium foil, the aluminium foil already has a layer of aluminium oxide on top of it. It's naturally formed when aluminium reacted with oxygen in the air. And the interesting thing about this layer is that it is impermeable. So what does impermeable mean? It means that water cannot go through it. All right. So what happens is aluminium, usually when you throw into acid, the reaction will be very slow. You can't see it. The main reason is because the aluminum metals below cannot react with acids immediately. Because in between the metal and the acid, there's this oxide layer. So why does it become faster? Well, if you know that what is slowing the reaction down is the oxide, now you can ask yourself, have I learned something about aluminum oxide? For example, if I throw this into acid, will the oxide react with the acid? So what have you learned about aluminum oxide? Aluminum oxide is what kind of oxide? Let's ask someone. Tiha, what kind of oxide is aluminum oxide? There are only 4 types of oxide.
Amphoteric.
Amphoteric. Right, good. So aluminum oxide is amphoteric. So it is able to react with acids and bases. So if you were to put this into HCl, the oxide will react with HCl, right? It's amphoteric. It can react with acids. So of course, the oxide must first react. After the oxide has reacted away, you are left with the metal. Now the metal can react readily with HCl. Because now the oxide layer has been removed, the metal is exposed. If the metal is exposed, it can react with the acid. And that's the reason why it's slow to start, but becomes faster and more violent to produce more hydrogen gas as it proceeds. So this is a trademark of aluminium. Whenever you read such a statement, you know that the metal is aluminium. So why is it that at home we don't see this? Well, at home you use aluminium foil to do a lot of baking, right? You can wrap up your food with aluminium foil, then you use an oven to go and heat the food up. Surely food contains acids. Yup. And that's the reason why when you use aluminium foil to wrap your food, you don't start to cook the food for very long. Because you know that once all the oxide has been removed, the aluminium metal below the oxide layer is actually very reactive. It could react with acid, steam, whatever that's hot, basically. Okay? Okay, so that is all I want to say about aluminium. Right? So please don't go away with the misconception. A lot of students think that, wow, because the teacher never mentioned, therefore aluminium doesn't react with acid. It's not true. Aluminium is very reactive. Okay, it will react very readily with acids. But it's just that it's slow to start. That's it. Okay? Okay, so now let's move on. Okay, I'm just going to do one last thing before we end today, and we'll continue on Wednesday. Okay, now, so the next type of reactions involving metals, this one actually you have learned before. You have learned it under group 7, right? You have learned that a more reactive halogen displaces a less reactive halogen from its compound. For example, you have learned that chlorine can displace iodine from its compound. So similarly for metals, it's the same. The more reactive metal displaces the less reactive metal from its compound. So a good example is magnesium versus copper. So if I put magnesium metal into copper 2 sulfate, what happens? Well, copper is together with sulfate, right? So it's a compound at the start. But the problem is, once you put magnesium metal in, magnesium metal is more reactive than copper. So magnesium metal can displace or kick out copper from copper 2 sulfate. Okay? So what happens to copper? It has been displaced. It has been left all alone at the end. And what has happened to magnesium is that magnesium has now combined with sulfate instead. Okay? So you know this is a displacement reaction when you see two metals, one as an element, one as part of a compound. So like at the start, magnesium is on its own element, and copper is part of a compound, copper 2 sulfate. So this is a competition between the two metals to see who is more reactive. Obviously, we know already from the reactivity series, magnesium is more reactive than copper. So it will displace copper. Okay? Now, what do you see? The observations, right? First, we can talk about a solid form. Copper metal is a reddish brown or pinkish brown metal. Okay, so we say there's a pinkish brown solid deposit. Deposit just means it's a solid formed that might sink to the bottom. Okay, then how about the color of the solution? At first, copper 2 sulfate, a copper 2 plus, is blue. It's a blue solution, but magnesium sulfate is colorless solution. So the color of the solution changes from blue to colorless. That's why we say the blue color of the solution fades. So you need to be able to describe these two things. The observations in displacement always two things. One, the solid. Two, the color of the solution. There are always two things you describe whenever you're asked what is observed or seen. Okay? And this reaction works because magnesium is more reactive than copper. So let's go through the table at the bottom, which is actually from the textbook. It looks very overwhelming, but it's really not so bad. Okay? The way to do this is to read row by row. Row by row. So we go to the first row first, magnesium. So if I put magnesium metal into zinc sulfate, then you can ask yourself, does magnesium displace zinc? Yes, magnesium displaces zinc because magnesium is more reactive than zinc, right? And that's why the equation you can see Mg plus ZnSO4 gives you Zn on its own. Zn has been kicked out, displaced, and now magnesium together with sulfate. All right. Now the solution remains colorless because both zinc sulfate and magnesium sulfate are colorless solutions. However, you see a gray deposit of zinc. Zinc is a typical metal. Zinc's color is just silvery gray. Okay. Then we have magnesium and copper 2 nitrate. Well, we already seen this, right? Magnesium is more reactive than copper. So magnesium will definitely displace copper. So what do you see? Well, your blue solution should turn colorless and you should have a reddish brown deposit of copper. Okay, copper metal is reddish brown, huh? And so on and so forth. Okay, so I shall not go through everything. But you can see that from these experiments, you can already work out which is the most reactive metal, right, of these 5. Quite clearly, magnesium is the most reactive. How I know that? If I read the data, magnesium is the most reactive because it can displace zinc, copper, lead, and iron. It can displace the other 4 metals from their compounds. That means magnesium must be the most reactive amongst these 5 metals. The least reactive will be copper. How do I know that? Well, from the data, you can tell. Copper cannot displace zinc, zinc, magnesium, lead, and iron. Copper cannot displace any one of these metals. Therefore, copper must be the least reactive amongst them. So this is another good way to do an experiment, plan an experiment to figure out the order of reactivity. Because from the results of the displacement reaction, we can work out, oh, magnesium can displace the other 4 metals. Therefore, magnesium must be the most reactive amongst these 5 metals. On the other hand, copper is unable to displace any of these metals. Therefore, copper is the least reactive. Okay? Now, please don't go and memorize this table. The point here is not about memorizing. The point here is, can you use this table to work out the reactivity of these metals? Next, can you actually work out, based on your knowledge of the reactivity series, which metal can displace who? Okay? Now with that, let's just move quickly to the next page. I'll just end off with the short question. So you can see, this is what I meant. This is a typical question, right? We can give you metals and the sulfates, and then you can work out what is the order of reactivity just based on the data. Okay, so this is a typical question. And we can also ask you what are the observations. So you can see part A is about the order of reactivity. Part B is about observations. What do you see, right? Which is what we mentioned just now. 2 things, right? The color of the solution as well as the solid formed. But let's look at part C. I hope you realize that part C looks slightly familiar from redox. And I hope you realize by now, this is obviously a redox reaction. Okay? Displacement reactions, as shown in part C, are redox reactions. They involve reduction and oxidation. So let's now zoom in on part C on page 14. And let's all look at the ionic equation carefully. Okay, they want you to explain this in terms of electrons, not oxidation states. So you now have to explain which substance has been reduced or oxidized using the idea of electrons. So let's try to recall. We have learned redox. We have learned the 4 definitions of redox, of which electron is one of them. We use the acronym OIL-RIG. Oxidation is loss of electrons. Reduction is gain of electrons. So now, using this definition, oil rig, what has been reduced? What has been oxidized? Let's take a minute to think first. Okay, so we have had about close to a minute to think about it after staring at the ionic equation. I hope we really focus on the charges, on the ions, because the charges will tell us roughly whether it has gained electrons or lost electrons. Okay, so let's start. Okay, maybe Jet, can you tell me what has been reduced?
Cu2 plus is reduced as it has gained electrons to form Cu.
Okay, good. So Cu2 plus is reduced. How do I know that? As Jess mentioned, it has gained electrons to form Cu, right? Now, how do I know that this is a gain of electrons? So you have to learn that when you gain electrons, you become less positive. So it went from 2 plus to no charge. It became less positive. So because the charge became less positive, I can conclude that it has gained electrons. All right. And Jet was also right. You need to tell me that Cu2 plus. It's not copper. Don't ever write copper is reduced. The substance is Cu2 plus or copper 2 sulfate, right? So give me the whole substance. Best if you give me the formula of the substance. Anyway, the equation is given to you. All right. Now, so Cu2 plus is reduced as it has gained electrons to form Cu. So now let's go to what has been oxidized. All right. Junwei, what has been oxidized?
The metal P,
So P is oxidized, right? So why?
as it has lost electrons to form P2 plus.
Yeah, that's it. Okay, so this is what you need to write to get 2 marks. So hopefully I've convinced you that a displacement reaction between metals, as well as between halogens, by the way, is redox. Okay, so displacement reactions are redox. In fact, if we recall, there are only 3 types of reactions in this world. 3 types, right? Redox. What else? We have precipitation, and we have acid-base neutralization. So there are only 3 types of reactions in this world: redox, precipitation, acid-base neutralization. So this displacement is a redox reaction. Okay. Now, so this is about using ideas about electron transfer. As you can see, we can test you either electron transfer, we can also test you oxidation states. So I would encourage you later on, try to work out this thing in oxidation states. And also convince yourself that if you had used oxidation states, you will come to the same answer. You will come to the same answer that Cu2 plus is reduced, P is oxidized. Okay. Now, my next question is, okay, so in this case, what is the reducing agent? Which one is the reducing agent? Is it Cu2 plus or is it P? So let's ask. Andre, which one is the reducing agent?
P is the reducing agent as it is oxidized.
Very good. So we have gone through this, right? The one that is oxidized, P in this case. So it tells you that P is the reducing agent. Because we have learned that reducing agents are themselves oxidized. Okay, so that's the intersection between metals and redox. Basically, every single metals question, if you look at the TYS, has redox inside. Okay, so redox and metals are really just one topic, if you like. Okay, so now let's make sense of this. Okay, so now we have made sense of the redox. Let's make sense of the reactivity. Okay, so based on this reaction, which metal is more reactive, P or copper? Okay, let's ask, Rishi, which metal is more reactive, P or copper?
Copper.
Copper. So if it's copper, then can P displace copper?
Yes.
P can displace copper. That means P is more reactive or less reactive?
More.
Okay, don't mute yourself. Come, let's answer.
Wait, P is more reactive than copper
So how do you tell?
because it lost electrons.
Okay. So, more importantly, how do you tell it's more reactive? Because it lost electrons. That's how you usually explain. Don't you have to explain in terms of displacement? So you know it's more reactive because P can
Displace.
complete a sentence. Displace?
Displace the electrons.
No, don't displace electrons. You displace.
Cu2 plus
You
Cu2 plus
displace.
electron.
Look at the next previous page. It can displace copper from its what?
So which one are you referring to?
The previous page, page 13.
Oh, page 13.
Magnesium is more reactive than copper because it can displace copper from.
Copper from its compound.
Yeah, so now let's go back to page 14, same page now. Okay. So P is more reactive. Why?
Because it can displace copper from its compound.
So what is the compound?
The compound is Cu2 plus. Copper 2 sulfate.
Yes. Okay, thanks, Rishi. Okay, I don't mean to put you in the spot, but I think this is an important process that we learn. Okay, we have to learn, okay, how to best manage, okay, our difficulties in phrasing our answers. As you can see, many of you, right, you will start to get confused between displace, redox, blah blah blah. So it's important to get the terminology correct. Okay, so just now we were talking about redox. So redox is about loss, gain of electrons. Now we talk about displacement, which is in terms of the reactivity. So P is more reactive than copper. Therefore, P can displace copper from copper to sulfate. Right? One metal displaces another metal from its compound. The compound in this case is copper 2 sulfate. Very good. At least you recognized it. Now, but in an ionic equation, it's not so clear-cut, right? You don't see any copper 2 sulfate in the ionic equation. So how do you tell if something is a compound or if something is a metal element? That's my next question. So in an ionic equation, it's complicated. You can't see a compound so easily. You go by charge. If it's charged, that means it's a compound. Because it must be part of a compound. You cannot have Cu2 plus on its own, right? The 2 plus ion must be balanced out by a negative ion somewhere else. Okay? So it is important to recognize in an ionic equation which one is the compound that you're talking about. So in this case, Rishi is right. Cu2 plus is part of the compound. It is part of copper 2 sulfate. Whereas when it has no charge like that, it's a metal element. And that's why we can say metal P displaces copper from its compound, because we know that Cu2 plus is part of the compound. All right, it's very important because you need to recognize from the ionic equations like these, very often, what is the compound. Many students didn't realize that Cu2 plus is must be part of a compound because they are not familiar with ionic equations. They thought that we must always give you a chemical equation. Nope. In fact, very often for displacement, we will just give you the ionic equations like these. So where did the sulfate go to? Well, the sulfate didn't go anywhere. The sulfate is present at the start and at the end. It didn't go anywhere. It is precisely because the sulfate ion is unchanged. It's still sulfate at the end. That's why in an ionic equation, we cancel out the ion that remains unchanged. So sulfate remains unchanged. That's why it got cancelled out. You don't see it in the final ionic equation. Okay. So P can displace copper from copper 2 sulfate. So P is more reactive than copper. So now my question is, if I were to do the reverse, if I put copper into P2 plus, will any reaction happen? So now I'm at the bottom here. If I do the reverse, that means I use copper metal, I put it into a solution of the sulfate of P, would any reaction happen? Okay, Audric, will any reaction happen?
No, the equation remain the same.
Oh, so nothing happened, right? No reaction. No reaction. Okay, let's try to explain why there's no reaction. How come when I put Cu metal, the metal element copper, into the aqueous solution of the sulfate of P, there won't be a reaction? We need to explain this. Well, we can explain it as copper is less reactive than P, right? So because it's less reactive than P, copper cannot displace P from its compound. So how do you know which one is a compound again? Look for charge. When there is a charge, that means it's part of a compound. So when you see P2 plus, that means P is inside the compound. All right. Whereas this is just the element. Okay. So you need to recognize this up. Okay. So the reverse, when you use copper with the aqueous solution of P, it's not going to work. It's no reaction because copper cannot displace P from its compound. Okay, so that is the end, okay, of what I wanted to cover today. Today we have covered the reactions of the metals with acid and the displacement reactions involving metals. Importantly, the main concept is a more reactive metal can displace a less reactive metal from its compound. So how do you tell from an ionic equation which one is the compound? As mentioned, charge. If it's charged, it's part of a compound. Okay, so in this case that's shown on screen, you can see that Cu2 plus is part of a compound. So P can displace copper from the compound, copper 2 sulfate. Whereas the reverse, if I use copper metal and the sulfate of P, there's no reaction, as you can see from the equation at the bottom, because copper is less reactive than P and cannot displace P from its compound. And we have also seen displacement reactions are redox. So you need to be able to explain which one is oxidized, which one is reduced. Okay, so that is really the gist of displacement. And we will stop here for today. The next lesson, we will finish up the remainder of the reactions after this. Okay, thank you.